Hi everybody, thank you for being here. So today we have Richard Healey, who is an emeritus professor of philosophy at the University of Arizona. Most of his current research is in the philosophy of science, and specifically the philosophy of physics, from a contemporary pragmatist perspective. He has recently developed his pragmatist approach as a form of agent-centered realism about quantum theory and defends the theory's objectivity against perceived threats. So the talk today is about pragmatism, relativism, and quantum theory, and there will be one more talk on Monday.
Tuesday.
On Tuesday, which is, I don't remember the title now.
Making it physical.
Making it physical, okay. So, if you're ready.
Yes, I am. So I'm really delighted to be back here at the Institute in Vienna, both of which are among my favorite places in the world, having spent a very happy summer here now quite a long time ago, 2009. I'm pleased to see it's still in the same building and many of the same people. Other people have gone on to successful careers around the world, which is nice to see. Okay, so I have to give thanks to the Institute for hosting this visit and to the Quantum Information in Space-Time collaboration for sponsoring it, and also to the John Templeton Foundation, who have funded the KEIS collaboration, and another organization with which I'm involved, namely the project What is Metrology if Quantum Measurement Participates in Making Reality? But I have to say that the views I'm going to express today are not necessarily those of the John Templeton Foundation. So thanks to all of those people. Now let's get started. So I'm giving two lectures. Today is more general and a bit more philosophical, and Tuesday's lecture is getting into more physical details, developing the same program. So what's the structure of today's talk? Well, philosophically, the interesting ideas are pragmatism and relativism. And the first part of the talk will be mostly concerned with pragmatism, starting out very general, and then using quantum theory, and in particular the use of probabilities in quantum theory, as an illustration of a pragmatist approach to a concept, namely the concept of probability. But then quantum theory will come in a little bit more. And in the second part of the talk, I'm going to focus on relativism in a very specific context, in the context of recent, very interesting no-go theorems developing the original Wigner's friend scenario into more extended scenarios, which, based on very plausible assumptions, derive a contradiction. One of the assumptions being the assumption that the outcome of a quantum measurement is a fact, or an absolute fact. One can avoid the contradiction by backing off that assumption and saying, no, it's only a relative fact, which is fine if we know what we're talking about when we're talking about relative facts, and if we know what they are supposed to be relative to. So those are the issues that will come to the fore in the second part of the talk. So let's go ahead then. In more detail, oh, nothing happened. That's strange. Why did nothing happen? Well, I don't have to use this. In more detail, this is going to be the structure of the talk. There's sort of a break in the middle where we stop talking about the pragmatism stuff and start talking about the relativism stuff. I'm going to start out very generally. What is pragmatism? What is pragmatism about science? Then I'm going to talk about probability and argue that it's objective, but it's relational in general, and specifically when it comes to quantum theory. I'll talk about quantum probabilities, and I'll argue that the same thing is true of quantum states, that they are also relational but objective, although they're not what John Bell called beables. Then I want to talk about a distinction between relational sentences and relative facts, which I think it's important to make if we want to be clear on what a relative fact is. And then I'll talk very briefly and in general terms about no results and extended Wigner's friend scenarios. Then I'm going to focus in a bit more. What is a relative fact anyway? I'll give you my take on what a relative fact would be. And in particular, what are the relative facts, if there are relative facts in an extended Wigner's friend scenario? What are they relative to? And finally, given that the existence of relative facts poses a challenge to objectivity, what can we do to rescue the objectivity of science? Amongst the alleged relative facts are facts about measurement outcomes. Facts about measurement outcomes are a very important part of the evidence for quantum theory. If they are not objective, we have no objective evidence for quantum theory. That would be bad. We think quantum theory is a very successful theory. We have lots of reasons to believe it. But if there are no objective facts, no solid data capable of providing the evidence for quantum theory, then it seems that we have no reason to believe it, which is a very unfortunate conclusion, which I will not draw. I will defend quantum theory and the objectivity of relative facts against a kind of relativist threat. Okay, so let's talk about pragmatism about science. And so I'm going to start out really general here. What is science anyway? Well, it's a human activity. Who are humans? Well, we're highly social animals, and we are situated in the natural world. So if we want to understand what's going on in science, we have to keep these important biological and social facts firmly in mind. We're very special because we use language. We use language to communicate thoughts and to coordinate actions. And there's a huge amount of this going on in the scientific enterprise, where we're exchanging thoughts about theories, coordinating our activities when performing experiments, and so on. Now, like other animals, we cope with our environment by representing it. We make models of the environment. We describe the environment. This is a strategy for coping with the environment. And as I say here, animals have this strategy too, even if they don't have language to represent. For example, there are specific cells in the rat's brain called place cells, which represent places that a rat may be in a maze. The rat can't talk, but its brain has representations of its environment that help it to cope with that environment. Back to humans. This representational strategy has been very successful in science. In physics in particular, where mathematics is extremely important in forming representations. But, and this is the point I want to stress here, representation is not the only way of using language. It's not the only way of using mathematics. If we have a model in physics, we can use it to represent physical reality, but we can use it to do other things as well. Okay, what other things? Well, I'm going to focus now on probability. This is an example of a non-representational strategy for using mathematics. So we use the language and mathematics of probability in daily life as well as in physics, and especially in quantum physics, which I'm going to move to shortly. So for a pragmatist, the important question is not what a probability represents, but what we can do with it. See, there's a focus on action rather than on representation here, which is not to deny that there is such a thing as representation, and in a weak sense, probability will represent something. But that's not the point of probability, to represent things. What is the point of probability? Well, here's a famous quotation, very old now, 1740. Bishop Butler, in one of his sermons, said this: "Probable evidence in its very nature affords but an imperfect kind of information, and is to be considered as relative only to beings of limited capacities, like you and me." for nothing which is the possible object of knowledge, whether past, present, or future, can be probable to an infinite intelligence, since it cannot but be discerned absolutely as it is in itself, certainly true or certainly false. But to us, probability is the very guide of life. That's what I want to focus on. Notice that he talks about limits to intelligence here. Those are not the only limits to which we are subject. We're limited by our position in the world. It's difficult to know the future. We are not clairvoyant, and so finding out about the future in general is much harder than finding out about the past. And as we live out our lives, more of what was the future becomes available to us. More information becomes accessible. That limit is gradually expanding, but it's still there at any moment. So anyway, how does probability guide us? Well, it guides us in two ways. It guides us as regards forming opinions, gaining knowledge, and here probability guides our degrees of belief. I'll call them credences, following a philosophical tradition where a credence is now a coherent degree of belief, such that a system of degrees of belief cannot put one in a position, if they are coherent, to have a bookie come up and propose a sequence of bets such that you're guaranteed to lose no matter what happens. That's a technical notion of coherence. So credences are coherent degrees of beliefs. And it's a principle of rationality that one should set one's degree of belief in something equal to the probability of that thing, if one knows it. That's the connection between probability and opinion, which is central to the use of probability. And practically, once one has some kind of opinions about things, that's going to be very useful in making decisions. Decision-making under uncertainty. We're uncertain all the time about all kinds of things because of the limitations of our access to relevant information. And probability can partially fill the gap. A simple example, when do you carry an umbrella? Only when there's a high probability of raining. It's really inconvenient dragging that thing around all day if it's not going to rain. But if there's a high probability of rain, then maybe it's wise to carry an umbrella. Another example, the half, yeah.
May I ask something?
Yeah, sure.
So if in contrast to the Bayesian, you distinguish the degrees of beliefs and probability.
Yes.
But you said you're not interested in probability as a representation of things. But now what is this probability which is not degree of belief?
That's an excellent question. In fact, on the next slide, I'm going to say we don't use probability to represent our degrees of belief. We use it to guide our degrees of belief. So what does it represent? There's not a very rich answer to that question. It represents probability. Probability is not something which corresponds to an element of physical reality, but it still exists. There are many things which don't correspond to elements of physical reality but still exist. Numbers, for example. Of course, somebody might deny that numbers exist and we go off on another tangent. But that's just one example of things which don't have an obvious physical correlate but still exist. So weakly, we can accept that probability represents something. Or more specifically, we have a number. And what does it represent? It represents the probability. Okay. So here's the second example. The half-life of technetium is 6 hours. So if you're going to use it in a medical test, you better use it pretty quickly. Otherwise, it'll be gone. I actually had a medical test in which I was injected with this substance at one point to do a stress test. So you run as far as you're able to on a treadmill, and with various chemicals in your body, including the technetium. They can track the flow of blood through your cardiovascular system. Yeah.
I don't understand this statement because you're saying that it's a principle of rationality that one should set one's degree of belief x equals the probability of x. But what is rational is also to recognize that be assigned probabilities. So I don't see why request.
Well, if you focus on the example, it seems natural. If you read in the morning paper that the probability of rain is 70%, then that's a good reason to take an umbrella. Not because you know it's going to rain, but because you think it would be wise to have a high degree of belief that it will rain.
That's not even probability, that's
Well, the probability that the meteorologist gives you is a probability, I think. Is that what you're denying?
I don't think it's a probability, it's a likelihood interval, right?
It's what instead?
It's a likelihood interval.
A likelihood interval? Well, maybe. But we can measure probabilities in different ways. We can measure it by a real number between 0 and 1, or we could have an interval. But however we measure it, it has the same function in guiding belief. That's the point.
Look, for instance, I can believe that in 20 years' time there are going to be whatever experiments doing
Right.
to show you something about gravity. Do you think there's a probability that can be assigned to that?
I would be reluctant to assign any such probability.
That's what I'm saying, but I still believe in it. So that's why I don't understand that when you have, why are you saying that when you believe in something, then there needs to be some probability that corresponds to it.
Well,
If you have a probability coming from
okay, let's look at the last clause.
then you assign your belief.
That's
Equal to the probability of x if one knows it. Now, there's two reasons why one might not know it. One might not know it because there is something of which one is ignorant, or one might not know it because it's just not reasonable to talk about a probability in this case. Okay, I think that's the best way to address your concern.
So in the cases where there is probability assigned, then you should believe in the probabilities.
You should set your degree of belief equal to that number. Right, right. Good, thank you. Okay, so let's see. So the first point I want to make is that probability is relational. When deciding how to act, the human or any other agent always lacks potentially useful information because of their situation in the world. Where are they? At what time is this information to be accessed? What physical blocks are there to accessing this information? In particular, they have observational access only to events in their past light cone, and they lack timely access to most of those because there are no suitable physical channels providing it. The point is that not enough information is accessible to determine the consequences of each of your contemplated actions. You have to decide what to do, but you just don't have the necessary information. And probability can help you in this situation by using what information is accessible as a basis for directly advising the agent on what credence to give to each possible outcome of any action. And again, probability can help, but sometimes we don't even have probabilities, and then we have to fall back on something even less informative than probability in deciding what to do. But all of this means that probability is inevitably relative to the agent's situation, because what information is accessible depends on that situation. And this is true in quantum theory in particular. We know that quantum states yield probabilities through the Born rule, and I'll give a statement of the Born rule. There's lots of ways of trying to state it. Here, rho represents a quantum state, and A is an element of delta, says that the value of a magnitude A on some physical system lies in set delta of real numbers. So I'm going to claim that Born probabilities comprise most of the empirical content of quantum theory. Maybe all, actually, but most of, anyway. So the main function of a quantum state, again, pragmatist says, what's the use of a quantum state? Its main function is to generate these probabilities. But since probability is relational, so is the quantum state. What quantum state to assign is relative because probability is relational. Now here I want to, again, distinguish myself from cubists. It's relative not to an agent, but to the physical situation with respect to which the assignment is made. And it doesn't matter whether there is any agent in that situation. If there is an agent in that situation, then the agent will be in position to benefit from the information provided by the probability. But it's there, whether or not there is an agent present to make use of it. So it makes sense to say that there are quantum probabilities and quantum states even in possible worlds in which there are no agents. That's fine. Nobody can benefit from all of that useful information in those possible worlds. Okay, next question. For quantum theory, what are these probabilities of? Well, we typically say they're probabilities of measurement outcomes. And we describe them as events such as magnitude A has a value in set delta of real numbers, or the polarization with respect to the A axis is vertical or horizontal. But Bell argued forcefully that the term measurement should be banned altogether in quantum mechanics as the worst of a list of words which have no place in a formulation with any pretension to physical precision. I was strongly moved by Bell's critique here. I think he's right. We don't really want to have this word measurement floating around in any formulation of quantum theory with any pretension to physical precision. But there are older no-go results which argue against taking A as an element of delta simply to describe a property a physical system has anyway. We have Cauchy and Specker theorem. We have Bell's work formulating a version of the Cauchy and Specker theorem, not formulating his own argument concerned with locality. So I'm going to take A as an element of delta to describe an event in which a physical system can be said to acquire a dynamical property after a suitably decohering interaction. But as we'll see, that leads to other problems. So dropping the word measurement, inserting the word decoherence hasn't solved everything, but it's made progress towards solving things, I think. I'll say more about decoherence in the second lecture. Now, what's interesting and where relativism comes in is the following, that recent no-go results give reason to think that a measurement outcome is itself a merely relative fact. Okay, so here's an example of Born probabilities that illustrates the relativity of probability and the relativity of quantum states. So consider a simple EPR-Bohm scenario in which we have a maximally entangled quantum state of a pair of photons, and we have polarization measurements in two space-like separated regions, 1 and 2. Left-hand photon is polarization measured in region 1, right-hand in region 2, and these PQs and Rs are all space-time points located, as you see. These sort of 45-degree lines are light cones to give you the relativistic space-time structure. Okay, so we consider the general case on the left, where EA is an event of measuring polarization of the left-hand photon with regard to axis A, and EB on the right is an event of measuring the polarization with respect to the B axis of the right-hand photon. Now, consider the specific case in which the two axes are the same on the right. They're both measuring polarization with respect to the same A axis. And I'm going to suppose that the outcome of the measurement in region 2 was that the photon was measured as vertically polarized with respect to the A axis. And the question is, what is the probability that the photon on the left will also be measured to be vertically polarized with respect to the A axis? And the way I phrased it suggests there should be a unique answer to that question. But in fact, there is not, because probability is relational. And the red numbers tell you what the probability is of that event relative to different space-time locations. So prior to the measurement of the polarization of the right-hand photon at point P primed, the probability that the left-hand photon will be polarized, measured as polarized vertically with respect to the A axis is a half. But after, in the future light cone of the EA measurement on the right, the probability is 1. It's changed. Okay. The red numbers here indicate what the probability is relative to each of those space-time locations. And the point is that it's different. There's no such thing as the probability of the left-hand photon being measured to have vertical polarization with respect to the axis. Yeah?
But there is such a thing as a probability at a given time?
What was the word?
The probability at a given time is defined, right?
No. The probability at a given time is not defined because, at least in the common lab frame, the probability at time t2 is different at p from what it is at q. So there is no such thing as the probability at a time. There's only the probability relative to space-time points.
At a time and at a place.
Yes, a space-time point or region more generally. Yes, right. That's an important distinction.
And the reason they're time asymmetrical is because the probability is something that we always assume is something that the agent would compute.
Yeah, because that's what probability is for. Exactly. Okay, so that gives you the story. It's just an example, and a particularly relevant example in quantum theory, of the relational character of probability. And it goes along with the relational character of the quantum state. So what is the quantum state that delivers up these probabilities? Well, we can use either the entangled state and then conditionalize on the outcome over here, or, more interestingly, to figure out what the probability of this being measured as vertically polarized relative to point Q, we can, as it were, collapse the quantum state onto an eigenstate over here. But that's not a physical process. It's a reassignment of a quantum state, which is necessitated by moving from probability relative to one location to probability relative to another location. Okay, so there's no physical process of collapse, but updating has to follow access to additional information, because that's the way probability works, and therefore that's the way quantum states work. Okay. So both quantum states and Born probabilities, in my view, and here again I'm disagreeing with cubists, are relational, but they're both objective, because the function of probability is to guide, not to represent degrees of belief. Probabilities have authority over any agent's credences, and that authority makes Born probabilities objective and not subjective, as cubists maintain. But if the probabilities, Born probabilities, are objective, then quantum states have to be objective too. They can't just be things in the agent's mind. On the other hand, well, put it this way. If the agent is following good advice, they will be in the agent's mind. But an agent can have anything they want in their mind that may or may not be related to the probability. And if it's not related to the probability in the appropriate way, then they made a mistake, in my view. All right. Of course, there's going to be a much longer debate with cubists on this critical issue. I'm giving you my view, and give me a cubist and we'll have a long argument. Okay. So quantum states have to be objective as well, because they yield Born probabilities, and if I'm right, they're objective. But they are also relative. So Born probabilities and quantum states are both relational, but they're both objective. It's okay to be relational as long as you're objective. That's why we're going to have a problem later when it comes to relative facts. Okay. So Moore-Bell, he introduced the term beable to refer to those elements which might correspond to elements of reality. to things which exist. And he spoke of the familiar language of everyday affairs, including laboratory procedures in which objective properties, beables, are assigned to objects. So in my view, quantum states are not beables of quantum theory, even though they are objective. A quantum state is not an objective property of a system. It's a relation it bears to a physical situation. Quantum theory introduces no beables of its own, according to my view, which I call desert pragmatism. Okay, why do I call it desert pragmatism? Well, the philosopher Quine had a preference for desert landscapes. He didn't like to have too much stuff in his ontology. He liked to be able to deny existence to lots of things. And so it seemed appropriate to call this view desert pragmatism. Also, I was in the Sonoran Desert when I developed this view, so that's another reason to call it desert pragmatism. The point is, there are lots of people around calling themselves pragmatists. And it's important to be specific about what exactly this pragmatist view is. For example, cubists owe a lot to pragmatism, and they have a different view to mine. That's why I need to just make that distinction. Okay, so quantum states aren't beables, but they are real. Okay, why are they real? Well, lots of statements assigning quantum states are true. I think I'm right, I might be wrong about this, that Laughlin won a Nobel Prize for coming up with a quantum state to describe fractional quantum Hall effect. So if they're not real, why did he get a prize? Yes?
Is it the difference you make from the previous slide when you said probability is objective, and
yes.
therefore quantum states objective? You go beyond that when you now say they're real.
I used a different word. How different is it? Something could be objective, but a statement can be objective but objectively false, right? And when we make a true statement about a quantum state, that quantum state is real. We can make false statements about quantum states too. Those quantum states are not real. So it's not quite the same, but it's closely connected to objectivity.
So I understood that it's objective because, if I may try to define, is that everybody, now I introduce agent for the purpose of the definition, I'm not saying it's necessary, but everybody who has the same access to the information about the context will assign the same state. That's why it's objective.
They should assign the same state.
Assign.
Maybe they won't. Maybe they'll make.
They won't.
Right. Yeah. Yeah.
They should, because then
Exactly.
they can test this and prove whether they are correct or not.
Yeah. Yeah.
And now, when you say it's real,
Well,
you don't think about some kind of a real field or anything like that? Or
no. When I say it's real, I don't say it's an element of physical reality. It's not an element of physical reality. But as I said in answer to your previous question, things can be real without being elements of physical reality. Yeah.
Right. So I'm just wondering how related it is to quantum mechanics per se, because there is a bigger question. As Richard said, he would take the numbers, natural numbers, to be real, to exist. I'm not sure.
Yes.
I sort of see what you mean, that somehow you don't want to call real things just, things like the chair and the table.
Right. Right. Right.
So what I'm wondering is if it's in that sense that you're saying that it's real, then I'm not sure this is a debate that has to do specifically with quantum theory. Because we can have this debate about numbers too.
Yeah. I mean, Frege had a view about the connection between truth and reality, as I understand it. So if one has come up with a true statement, and in that statement there is reference to, apparent reference to some entity, then if the statement is true, the entity exists. It's real. It's just a very straightforward connection between truth and reality that I'm relying on to say that. So, like as I say here, many statements assigning quantum states are true. If they're true, then the quantum states are real. There's nothing more to be said. And what's interesting is that this includes statements assigning two superficially incompatible quantum states to the same system. They may both be true together, since they state the system's relation to different situations, and a state may be assigned relative to either of them. We saw examples of this in DPR bomb scenarios, where at a single time in the lab frame, different quantum states were assigned to a single system. In that case, one of them was a pure state, one of them was a mixed state. But there are even cases where you should assign distinct pure states to a system, each relative to a different situation that some agent may or may not be in. There's a nice example of this that I found in a paper of which Adán Cabello was a co-author, that appeared in Advances in Physics last year in the spring sometime. The particular experiment that he referred to didn't quite fulfill this, because the relevant state descriptions were not at space-like separation. But you could make them that if you did a fancier experiment. Okay. Okay, so that was the second to last bullet point. So what does a quantum state description do? It doesn't offer you a different perspective on the system's condition. That's not what's going on. Instead, it reliably guides the credences of a differently situated agent. That's what it's doing. Okay. So at first sight, it seems crazy to say, well, it's correct to assign two different pure states to a system at the same time. That sounds crazy. But if you see what quantum states are doing, then you can see that there are situations in which that's correct. Okay, now I'm going to move towards the second part of the talk. And I want to distinguish between relational sentences and relative facts. Okay, so let's start off with some relational sentences. 2 is greater than 1. The Earth is about 150 million kilometers from the sun. Okay. Those are both relational statements. The first one relates two numbers, and the second one relates the Earth and the sun. Those are both facts. I used the first two sentences on this slide to state those facts. So here we have two relational sentences, and we have two facts. Each sentence is relational in form, but neither fact is a relative fact. They're both absolute facts. I mean, think about it for the moment. That 2 is greater than 1 is an absolute fact. It doesn't depend on anyone or anything.
Depend on the axioms of the Peano axioms?
Well, we could have something like Peano axioms and prove it from them. Yeah, we could do that. But then why do we accept the Peano axioms? I mean, because it delivers up truths like that.
Yeah, but you don't have to. You either accept them or you don't, right?
You don't have to accept them? Okay. So there's an alternative set of axioms that somebody could start from that would deliver up different theorems. That's easier to make sense of in the case of non-Euclidean geometry, I think. It's hard to come up with serious alternatives to Peano axioms. But certainly it's easy to come up with alternative systems of geometry than Euclid's. And that raises the interesting question, what is the status of, say, the parallel quote-unquote postulate? Is that a fact? Does that state a fact? Well, then we get off into the philosophy of geometry and Poincaré and conventionalism. And it's a very interesting discussion. But if you don't like that example, come up with one that you do like.
That's not what you mean. I mean, you're saying that because my issue is that somehow what is 2 and what is 1 is a definition, right? There's like definition you make that have this property. So maybe that easy of stating as facts things that we just make up. So we define something and then we call it the fact. But maybe what you mean is that it's having laid out the axioms, what you know what is 2 and what is 1 and so on.
Mm-hmm.
It's not that it's not going to depend on any context or any.
Right. It's going to be important here to distinguish between what follows from axioms and what is true. We know enough about axiomatizations to know that there are truths that are not captured by any given axiomatization. That's what Gödel showed, right? So we have to be a bit careful. I'm talking about truth. I'm not talking about theoremhood. But the point I'm making is general. Again, if you don't like that example, substitute your own example that you do like. The point is that if you come up with an example that satisfies you, it will be an example of a relational sentence which is true and which states an absolute fact. That's what I'm after. Okay, what about relativity?
Something like, I am younger than you.
That will do.
That's right.
Yeah.
That's a relationship. That's a relation, right? It's a relation. But it's like, I'm shorter, or I'm shorter is a relevant fact, maybe. But I am shorter than you would be like.
I understand. I just think that the use of the word absolute is too strong. So, because in order to say this, we have to first sit down and agree between us what we mean by all these words and everything.
There's another thing I could try here. Talking about absolute it seems to have a kind of heaviness, like a metaphysical weight. Just get rid of the word absolute. It's a fact. Just stop there. Okay, it's a fact. It's not a relative fact.
I find intriguing that when one tries to define this, one doesn't go away from agents and observers, in my opinion. Because other one would say this is a metaphysical truth, and so don't ask me about it. But if I try to operationalize this,
Yeah.
I would say, as you said, it doesn't depend on anyone or anything. So
Right.
all agents will agree on the same fact. And
We hope.
I find it very intriguing that whenever you try to understand what is even signaling, you have to use this help of maybe hypothetical observers, if not real, in order to define things. Although I don't think they are relevant, but I don't know how to operationalize.
That's interesting. I'm not sure how important it is to operationalize this. I mean, it's a natural physicist instinct to want to operationalize things, but I don't think mathematicians would share that instinct.
Then I would ask you really what you mean with that.
Okay, I'm prepared to drop the word altogether, and then I don't have to tell you what I mean.
It does not depend on anyone and anything, and that's the definition.
Okay, I'm happy with that.
Maybe I think the point can be that there is one kind of fact, and that has some property, and then there is another kind of fact that does not have that property. Then you can call them whatever you want.
That's for sure. Yeah.
Question is, what is that property that differentiates between these types of facts?
There's lots of room for differentiation and distinction, sure. So what about relativity theory? I mean, the word relativity is right there. So maybe we have relative facts in relativity theory. I don't think we do. But we have to go slowly to see that we don't. In relativity, distance does depend on a choice of reference frame. But I typed the second sentence here, the Earth is about 150 million kilometers from the sun, while moving roughly inertially with the Earth in its rotation. And by default, that picked out the frame in which I typed it, and so determined what fact I stated by using that sentence. So there's like a default that the use of the sentence here is in a context defined by the state of motion of the one who uses the sentence. And that's why what I said was true, and therefore what I said stated a fact. On the other hand, suppose somebody used the same sentence while passing the Earth towards the sun at 3/5 the speed of light, if they used that sentence, it would not state a fact, because that statement would then be false, because they're in a different state of motion from me.
What sentence?
So, I mean, for somebody who passed me as I typed that sentence towards the sun at 3/5 the speed of light, if he uttered that same sentence, what he said would be false, because his reference frame is different from mine. So the context in which he used that sentence by default picked out his reference frame. And in his reference frame, if I got my calculations right, the distance between the Earth and the Sun is 187.5 million kilometers, not 150 kilometers.
Sentence about the Earth. Okay.
So the point here is that in relativity, we have absolute facts, but we have to express them differently in different frames. And there's no relative facts coming in at all. It's just the same facts. And we have like a translational manual that tells you from my way of stating the fact to your way of stating the fact. But we're both stating the same fact in different words. I think this is right about quantum states too. When you assign a quantum state, you're not stating a relative fact. I won't go through this in detail, but you can read the transparency for yourselves here, just to speed things up a bit. A quantum state is relational, sure. A true statement assigning a quantum state relative to a specific situation states a, I didn't use the word absolute this time, plain, non-relative fact. Okay. But it's a bit different from relativity, because no relativity principle permits you to transform between quantum state assignments relative to different situations. So it's not quite the same as relativity theory, even though we don't have relative facts here. Okay, so finally let's get on to the extended Wigner's friend scenario. For those of you, if there are any in this room, who are unfamiliar with this, in 1961, Wigner used the Gedanken experiment to argue that differently situated observers who each correctly applied quantum mechanics would reach incompatible conclusions about the outcome of a quantum measurement performed by one of them. And in recent years, extensions of Wigner's scenario have been used to prove related no-go results that are stronger than his, because they are based on more readily defensible assumptions. So the way I see it, each of these no-go results arise at a contradiction, starting from various plausible assumptions, thereby challenging each of these assumptions individually, certainly collectively. And one way of getting out of this contradiction is to take the outcome of a quantum measurement to be relative to the observer that makes it, to be a merely relative fact. Yep.
So to have to just to get the point. So, okay. So how is this now different than the example you gave before? That depending on how I move, you know, I can either state correctly the distance with respect to me, that's a fact, or no, that's not a fact. So what is the fundamental difference here? You want to say that this is a very different situation?
Yeah, yep. I don't have all of the stuff laid out yet to give you a good answer to that question. So I think it's probably best if we go on, but don't forget it. I'm not trying to slide by and not answer it. Okay. Okay. But let me just point to the worry that this raises. Look, this poses a relativist threat to scientific objectivity, insofar as it implies that we can't agree on the observed facts we take to justify belief in quantum theory. That's the real problem. I mean, we believe quantum theory based on records of measurement outcomes and looking at statistics and showing that they match what we'd expect from the Born rule. But if those measurement outcomes are not even facts, because they depend on the observer, then my take on the measurement outcomes might be different from yours, such that we can't even agree on the data as to what the recorded measurement outcomes are. If we can't agree on the data, then we have no objective evidence for the theory. So we don't have any reason to believe the theory, which is a disaster because we have great reasons to believe quantum theory. So something's gone wrong somewhere. That's the threat. At the end of the talk, I'm going to say what we can do to address that threat. But at the moment, I want to get you worried so that there's some point in continuing along this road. Okay? Yeah.
Maybe this is premature too, but in the context of this thought experiment, isn't that agents disagree on whether there is a record of it?
No, it's worse than that. They must disagree on what the record recorded. One must say that the photon was recorded as vertically polarized, another must say the photon was recorded as horizontally polarized.
Although they can never actually compare their...
Exactly, yeah.
Oh, I am not sure I would agree with this statement, but
okay.
Because this is our talk, like this is the same measurement of opposite results. I never saw an overall theory.
I think you are forced into that, but we should talk about this later because it's an important point. Shall I continue?
Yes, please.
Okay. Okay, no, sorry. Okay. So, very briefly, to derive a no-go result, you begin by describing a suitable extension of Wigner's original Gedanken experiment. And because that involved his friend as a second observer, these have been called extended Wigner's friend scenarios, or EWFS for short. So a minimal requirement of an observer here is going to be the capacity to perform and record the outcome of a measurement on a quantum system. That means that an observer in an EWFS is also an agent. He has to do something. And my view takes the Born rule to apply to events in which a system acquires a dynamical property after a suitably decohering interaction. Measurements involve such interactions. But the point is, they may also occur naturally, where nobody's actually measuring anything. A measurement outcome purports to be a fact produced by a measurement event in which a system acquires a dynamical property. That's what it's supposed to be. So if these are going to be relative, what are they relative to? Well, people say they depend on the observer, or they're relative to the observer. But we have to be a bit careful here. What does that mean? Does it mean there will be no measurement outcomes if there were no observers? Or does it mean, as Wigner thought, that it's the observer's consciousness that creates an outcome? No. At least according to desert pragmatism, some events in which a system may be said to take on a dynamical property occur without the help or even the existence of any observer. There don't have to be observers around performing measurements before these events occur. Facts to which these events give rise, if that's true, cannot depend on any observer. So why should a measurement outcome that is produced in the same way? So I'm arguing that it's not relative to the observer. That's not what matters. It's relative to something more physical that could go on even if there's no observer around. So any relativity of a measurement outcome would not be to an observer, but to a context given by the physical situation of a merely hypothetical observer. And that's going to be a topic for the next lecture when I tell you what kind of situation that would be. Okay, sorry. So now let's talk about the difference between facts and relative fact. Now, I got a bit of resistance on this, but I claim to have argued, at least, if not convincingly, that neither the use of relational sentences nor the theory of relativity forces us to acknowledge any relative fact. So why would quantum theory? What's special about quantum theory? And what is a relative fact anyway? What are we talking about when we're talking about relative facts? Well, all the facts we've encountered so far are not relative to anything beyond what statement is made by using a sentence in a context. So let's talk a bit about context. If you make a statement by using a sentence in one context, C1, can be true when assessed at, or with respect to, context C2, but not when assessed at, or with respect to context C2 star, then the statement assessed as true in C2 may be said to state a relative fact. Okay, that's a bit of a mouthful, right? There's two kinds of contexts that are involved here. There's the context of use, and there's the context of assessment. And those contexts in general have to be distinguished, and relative facts come in when whether something is true when assessed at one context, when it happens that a sentence which is true when assessed, a statement that is true when assessed at one context is not assessed as true when assessed at a different context. So what's going on there? What would be an example of that? Well, there's a form of relativism which has been defended by a philosopher, John McFarlane, which gives a framework for talking about this, and he illustrates it by an example involving different assessments of taste. So apparently some people like licorice and some people can't stand it. Right? So there's two people here. There's Yum, he loves licorice, and Yuck, who can't stand it. Yum asserts that licorice tastes good. That's the statement he makes. Yuck denies this. Licorice does not taste good. They disagree about whether licorice tastes good, and they assess the truth value of the proposition that licorice tastes good differently. In Yum's context of assessment, it's true. In Yuck's context of assessment, it's false. That licorice tastes good is a relative fact at Yum's context. That licorice does not taste good is a relative fact at Yuck's context. There is no absolute fact about the taste of licorice on this view. Now, this is a possible example. I'm not sure that McFarlane is actually right about this case. He has received criticism. But if he's right about it, this is a good illustration of when it's a good idea, when it's necessary to talk about relative facts. You had a question?
Yes, because there is a presupposition here, right, that it makes sense to talk about the taste of licorice. Because I could say that, no, it's not that they're relative facts, it's just that there are two absolute facts. One being that licorice tastes good to Yum.
Right.
The other, that licorice does not taste good to you.
Right, that's an alternative way of responding to this situation. I think that what McFarlane would say, if somebody took that line, would be, if that's the correct resolution of the situation, there is no longer any disagreement between Yum and Yuck. And McFarlane thinks that's wrong. A disagreement remains. There is something about which they are disagreeing. And therefore, the approach you were suggesting doesn't give a correct account of the phenomena. That's what he would say. I'm actually somewhat with you.
But they can agree that they are in disagreement.
Okay, so would they then agree to disagree, as we say? McFarlane says no, they just disagree. Okay, so that's why this is a controversial example. But I wanted to give you an example that had nothing to do with physics, so that you see the generality of the framework that I'm using. Okay. Okay, so what's the difference between, now I'm stopping using that dirty word absolute, right? Between fact and relative fact, okay? Well, I'm taking what's called a deflationary view of truth, Pragmatists are sometimes accused of giving a pragmatist theory of truth, which is then criticized by people like Bertrand Russell. But actually, there are many pragmatists' approaches to truth. Charles Peirce, the founder of pragmatism, had a different view of truth. Frank Ramsey, who was influenced by Peirce, had a different view of truth. There is no one pragmatist view of truth. I'm taking a deflationary view of truth, which has a lot in common with Ramsey's view of truth here. Okay, so on this deflationary view of truth, plain non-relative notions of truth, in fact, may be characterized by these two principles. A statement that P is true if and only if P. Short and sweet. Fact, a statement states a fact if and only if it is true. Again, short and sweet. Once we have those on the table as what we're talking about when we're talking about truth and facts, then we can move over to try to make sense of relative truth and relative facts by just inserting a little bit more. Relative truth, a statement that P is true relative to a context of assessment C if and only if P relative to a context of assessment C. Relative fact, a statement states a fact relative to C if and only if it is true relative to C. And again, let me stress here that C is a context at which a statement is assessed, not a context in which it is made or used. So now we have a framework for talking about truth relativism. A variety of truth relativism is associated with the class of statements and contexts for which no plain notion of truth and fact is applicable, but only notions of relative truth and relative fact. That's what makes it radical. We tend to think that the notion of truth and fact is universally applicable, but if you're a truth relativist, you think that there are situations in which a simple, plain notion of truth is simply not applicable. And you have to, as it were, fall back on a notion of relative truth as the only one that has application in that situation. That's the kind of thing that never happens in relativity theory, if I'm right. Okay, so back to extended Wigner-French scenarios. To repeat, a no-go result demonstrates under apparently plausible assumptions that a series of measurements by multiple observers in that scenario cannot, probability 0, each have a unique definite outcome. Now there's a bunch of different extended Wigner-French scenarios and related no-go results around there, out there now. In every one that I know about, and if there's one I don't know about, of which the following is not true, please tell me. Right. In everyone I know about, some of these measurements are to be performed by an observer on a system that includes another observer. And that makes realizing one of these things experimentally extremely challenging, if possible at all. Because most of the time in the lab, you don't make measurements on observers. You make measurements on physical systems. And it's important to stress that all measurement outcomes here are supposed to be actually observed by some observer in an extended Wigner-French scenario. We're not talking about sort of hypothetical or counterfactual observations. It's also important that no observer in one of these scenarios ever has records of all of them, and that some records are actually destroyed during the Gedanken experiment itself. Okay. So it's a very peculiar situation. I mean, Gedanken experiments are really interesting to think about, and this is one. But this particular kind of Gedanken experiment is incredibly difficult to realize and has some very strange features. Normally in an experiment, you think that all of the records of what happened are available for perusal afterwards. In this case, no. Some of them have been deliberately erased during the course of the experiment. Yeah. Okay.
That multiple observers in that scenario cannot each have a unique definite outcome. One way of reading, for me, of this scenario is that there could be scenarios that each observer does have a definite outcome. that one cannot combine these definite outcomes as being all
Yeah.
or even joint probability for that.
Okay. Perhaps I was a little incautious the way I put it. Cannot each have a unique definite outcome? What I meant to say was that they cannot be combined. Perhaps the way I put it suggested that that was not what I meant to say. Okay. So I'm going to say something now which maybe people will disagree with. I can learn something from disagreement here, I'm sure. I know of two strategies for deriving a no-go result in one of these scenarios. Czeslav's, I should tell you guys, he's one of the big movers in this field, right? He's come up with more than one such argument. His original strategy depended on a locality assumption that made it feasible in principle for some observers to amass enough statistics to compare against quantum predictions in the form of a Bell inequality at the end of the experiment. And that strategy subsequently led to other no-go results that depend on weaker assumptions. In particular, there's a paper by a bunch of authors. The head author is Bong, but also Howard Wiseman and Eric Cavalcanti and a bunch of other people contributed to this paper. But there's an alternative strategy, I think, that doesn't require any locality assumption. But it has an unfortunate drawback. It would not permit any observer to amass enough statistics of the assumed measurement outcomes to permit an experimental test. Since too many records will be destroyed in the course of the experiment. There's a couple of Duncan experiments along these lines. One, according to Matt Pusey, was proposed by Luis Massanes and further developed by me. And another argument was proposed by a young philosopher of science, Keith Ligwater. And if I'm right, these arguments don't rely on a locality assumption, but all you get is a reductio. Assume these premises, you get a contradiction. You don't have the possibility of implementing it experimentally, because any experimental implementation would already have destroyed too many records for you to look at them at the end and see that, that there's a problem, right? Okay. So let's talk about objectivity. And here I'm really not sure I got it right yet, but I'll tell you what I think today. What is objectivity? The first thing to say is that objectivity is not the same thing as intersubjectivity. Frequently, especially when I talk to physicists, they think they have a much better grip on the notion of intersubjectivity than they do on the notion of objectivity. Intersubjectivity is, we all agree on this. Okay. Objectivity is not quite that. First of all, we don't all have to agree. There might be sort of outliers who don't agree, but it still could be objective. Why is it objective? Because it's something that has authority. This is what you should believe. So I think that objectivity is instituted by social norms. The norm of collective agreement is what institutes objectivity. It's not constituted by correspondence to reality. That's the important thing. There's an alternative perspective on objectivity. Something's objective if it corresponds to reality. Okay. But we never know whether anything corresponds to reality. We do our best to find out. Objectivity as instituted by social norms is something that we can get a handle on, because you feel the community pressure, as it were, to agree to something. And there are reasons why it's good to respond to that pressure in general, although in any particular instance you might end up being wrong. So I take it that it's a scientific norm to require a consensus on the data that provide evidence for or against a theory. If you can't agree on the data, why should anybody agree on the theory that's supposed to be supported by the data? Once you reach a consensus on the data, then the data are accepted as objective. That's what objectivity means, as it were, in practical terms in science. These are the data that we all have reached a consensus on accepting as the data that we use as evidence for or against our theory.
But isn't this precisely subjectivity? Like when we reach a consensus, we all agree that these data are objective.
No, that's an excellent response. I mean, more has to be said, right? I guess the perspective I have today is that each of us individually forms beliefs on the basis of our own individual experiences, and also on the basis of testimony that we get by listening to what other people say, and reading textbooks, and going to lectures, and all that stuff. I mean, very little that you actually take yourself to know is material that you have, in which your knowledge is based on your own direct experience. And when you fold all that other stuff in, then you're inevitably being swayed by social norms. And that's all good. And at any point, you may be mistaken. But of course, science is fallible. So any of us, all of us, could be mistaken at any point. Right. Okay. So let's look now at the relative facts in a no-go scenario. This is the last substantive slide, so I hope Marius can stay for this one. Anyway, first point, no consensus can actually be reached on the outcomes of all the measurements in a no-go extended Wigner-French scenario, since no one can access them all. So there's no possibility of consensus here. Physics rules against it, as it were. And the no-go result may be taken to show further that there cannot be any facts about these outcomes on which to seek consensus. Well, taking them to be merely relative facts avoids the no-go result. That's good. But still, what is true about some outcome at one context must be false at a different context. This is what we were talking about earlier. I think that is true. So observers associated with different contexts could not reach consensus, even on the relative facts in a no-go extended Wigner-French scenario. These relative facts are not objective in an extended Wigner-French scenario. And that's bad if we ever find ourselves in extended Wigner-French scenarios. But I don't think we ever will. Yeah?
No, I'm trying to think about that. But isn't it that these relative facts can be still shared within the context by many observers?
Oh, within a context, sure. Yeah, but then there's another context with its observers with which they cannot be shared. Correct. Thank you. Yeah, we tend to think there's just an individual in each of these labs, but there could be a whole community. Okay. There are currently no extended Wigner-French scenarios in our world, and my view gives us strong reason to think there never will be any. Why? Well, realizing an extended Wigner-French scenario requires a kind of conspiracy between two individually extremely difficult requirements, and they have to work together. It requires a high degree of temporary isolation of local environments, which we could call laboratories if we like, interrupted by periods of intense, precisely choreographed interactions among them. I believe that neither of those requirements will ever be met in our world individually, and moreover, they're in tension with each other. You have to be able to switch off all interactions when you need to, and switch on very carefully choreographed interactions when you need to. Now, I have to be careful here. An extended Wigner-French scenario is not excluded by any physical law. It's not physically impossible. That's not the reason why it's never going to happen. But neither is this impossibility merely technological. You know, it's not just that we don't have the technology today and we don't have a clear path to developing it in the next century, say. It's worse than that. if I'm right, it's ruled out by contingent but pervasive and irremovable physical features of our world. Our world is such that there are lots of decoherence processes going on all the time, which we cannot adequately shield against or remove. And that is going to make it impossible for us in this world to perform an actual extended Wigner's friend experiment. So if that's right, we actually can reach consensus on the relative facts about measurement outcomes at the one context we come to share. We're all stuck in the same boat, if you like, because of physical features of our universe. And that boat is one in which we can't perform an extended Wigner's friend scenario. So we'll never be faced with this really unfortunate situation. We do have the objective data that warrants us in accepting quantum theory, because in the context that we all come to share, or at the context that we all come to share, the relative facts are such as to provide that objective data. So quantum theory is okay, if this is right. We do have the reasons we always took ourselves to have to believe the theory based on the objective data provided by the measurement outcomes that we have shared and accepted as objective. Okay, so that's it, and here's a summary of what I said today. I'm sorry if I took too long, but the follow-up will go into the details that weren't discussed today. What exactly does decoherence do for us here, and how does it do it? How can we all agree on the outcomes of the experiments that have been performed that we take to provide the data to support quantum theory? Thank you for the opportunity of talking to you today, and I look forward to lots of reactions, and I hope to learn from all the criticisms I expect to get.
So let's take some questions. Thank you, Richard, for the very nice talk. Let me give you the microphone so that
Hi. So thanks for the talk. I wanted to comment on like the kind of pragmatic solution that somehow you give to the fact that certain extended Wigner experiments would lead to this lack of objective consensus by saying, okay, but this is not somehow I understand it. This is not the world we live in, and therefore we shouldn't be worried.
Right.
I try to connect this with the first part of the talk in which you mentioned like somehow like the contingent nature on how we derive our physical theories. No, we happen to derive classical mechanics because we happen to live in a certain world where we hadn't been exploring certain regimes, and we came up with this solution. In this sense, I believe that quantum mechanics, it's going to be as much contingent as any other. But maybe then the use of these extended Wigner experiments would be, okay, maybe not by doing an extended Wigner experiment, but doing something maybe easier.
Yes.
We can come up with the limits of the theory. And this could be a guidance on finding out the limits of quantum theory and finding out possibilities of experimental realization of them. I don't know if you agree with this usefulness of the thought experiment.
Yeah. No, I'm very much in agreement with what you said. We have enough experience from the history of physics to know that it's unlikely that we presently have the last word. And so we're always looking for situations in which our present theories are going to break down, because then we might be able to develop better theories in future. And in this, with this perspective, we want to learn from anything that might guide us in performing actual experiments that might lead us to a breakthrough towards some new and better physics. And if the extended Wigner scenarios do that, great. So I don't want to be taking a wholly negative attitude towards any experimental program that would lead us closer and closer to performing an extended Wigner scenario. So that's the substantive answer. We're very much in agreement on that, I think. But there's one thing you said right at the beginning, and I meant at the beginning of my talk to address this point. You used the word pragmatic, and people often call my view pragmatic. Even philosophers do, and they have no excuse, because pragmatism is a well-developed tradition in philosophy, and pragmatism and pragmatic are completely different things. So it's a mistake to call my view a pragmatic view. It's a pragmatist view, because it draws on a rich, although conflicted, philosophical tradition that goes back to Charles Peirce and William James, but has been pursued on both sides of the Atlantic by a bunch of people. And I'm particularly influenced by contemporary pragmatist philosophers, not by William James or Charles Peirce. That's a very minor comment. The substantive part of my response was the earlier part.
Thank you.
Next question.
Thank you, Richard. I think this is maybe a technical point, but
Yeah.
I was thinking about the last statement about this story about, so let me just break down. On the experiments, on the extended Wigner scenarios, no coherent that I'm familiar with mostly, which are the Chaslav-Bong version.
Yeah.
The theorem doesn't rely on people having different understanding of the result of a measurement. Like, people don't disagree on the result of a measurement. They disagree on whether there is a measurement or not. They don't disagree on the value.
But in the best scenario, they can perform in every run a measurement, or one of them is performed, or both of them is performed. But I think your question is, I want to pose the same question. It's not that there is one measurement in which they disagree on whether the outcome is up or down, because one measurement is one context. It seems like impossible for me that they disagree on this one measurement. But what they disagree, or I don't know, I wouldn't say you can disagree. Every each of them sees something, believes this, and everything like an ordinary quantum mechanical situation. It's just that there is no underlying joint probability for all
Okay, okay.
So different measurements.
I think we should pursue this further in discussion. It may be that the two different strategies I outlined go different ways on this. That the strategy that can't be experimentally implemented will give you a straightforward contradiction. It was up, it was down. But maybe the Chaslav-Bong strategy doesn't give you that. I'm not sure how significant that is, and I'd like to understand this better than I presently do, and you may well be right about that.
So I don't want to take now subject of your next talk, but but can you, so somehow context is very important in all this.
Yeah.
Talking and the relativity of these outcomes with context. Can you say something about how you? I mean, I have my own problems with this, so I don't. Like, what counts for context? What is a context?
Oh gosh. Well, it's a very abstract notion within truth relativism that can be have many different concrete realizations. In this context, where I want to implement a truth relativist approach to relative facts in extended Wigner scenarios, it's going to be defined by the type and extent of decoherence. And in particular, a decoherence context will, in general, differ. For example, when you switch from the interior of a laboratory to the exterior of a laboratory. So you can see how physically contexts are changing here. I mean, there's another wrinkle which, no, I'm not going to say that. I'll say it in the next lecture. We have to be very careful because of the way I think of decoherence as a model of which can be deployed in various ways. It's not actually telling you physically what's going on, and that's another subtlety we'll get into in the next lecture.
Okay, and maybe just to follow up.
Yeah, please.
It's not going into, I guess, the same direction. Is, I mean, going back now to here's Andrea and Carlos, relative effects. They would assign this. I don't know whether Andrea is still subscribing this, but even if there is no decoherence, like a fact about one system relative.
Yeah.
Would you go that way, or?
No, I would not. I mean, again, this is going to come out in the next lecture. There are different ways of relativizing things, and relativizing it to some other physical system with which a system has previously interacted, I don't think is going to work. So I would disagree with relational quantum mechanics on the issue of what things are relative to. And also I would disagree with cubists on what things are relative to, because I think for cubists things have to be relative to an agent. There has to be an agent there for there to be anything for something to be relative to. In my view, that's wrong. There doesn't have to be an agent there. But there has to be something more or different than just some other physical system, in my view. So this is a substantive disagreement between otherwise fairly closely related approaches to these issues. Yes?
Another question?
Thanks for the talk. Like I have a question about this statement where one says it tastes good and the other one says it tastes bad. And like one objection kind of that I would like to make is that this seems like a statement you cannot really test, but you can kind of turn it into a statement that you can check.
What is the statement? I didn't get that yet.
No, like, okay, this...
Oh, length, yeah.
There was this food, like, or this thing, and one agent says it tastes good, the other one says it tastes bad.
Oh, yeah.
About licorice.
Right, licorice, yes.
So that only works for the internet, so you need to talk loud for us to hear.
Alright, okay. Okay, but now, like, you can turn it into a statement that you can kind of check. And for example, you can ask, like, there's a third person, and then you can, there are two options. Like, the third person says it tastes good or it tastes bad. And now these two persons here, maybe they have a different, or they would assign a different probability to the fact that, like, the third person will say it tastes good or bad. And now, like, would these two persons, like Yam and Yak here, like, agree on the probability that the third person says that it tastes good? It's also a bit connected to Armand's theorem, like, if you are familiar with that. Because, like, that seems to me to make a big difference. Like, if you can perform like a test.
That's interesting. The way I understand the example, they need have no opinions whatever about what anybody else would say about licorice. They're just the two of them, and they don't care about anybody else. They're just, so as it were, defending their own view of licorice. They may have opinions as well. So if they did, then we could use those opinions. We could throw them into an enriched presentation of the example and see what effect that would have. Yeah. So your proposal was that if we do allow them to have opinions, then that might take the form of having different personal degrees of belief about what somebody else would think. All right. And how would we continue from there? Is this supposed to resolve the disagreement somehow, or dissolve it? What would the significance of those further opinions be here?
Okay, like in a bigger context, maybe like this Armand's theorem,
right?
Like, which basically says you cannot agree to disagree. And what it means is that, like, if there are two persons, and it's kind of okay that they assign different probabilities to a certain event,
right?
Because they can have different information. Like, for example, like two persons that discuss if there will be rain today, then are just look at the sky, I would say it's not going to rain, but maybe you have more information and like looked at the weather forecast. And then you assign a certain probability to the fact that it will rain today. And then like discussing with you, I will realize that you will assign a probability, and then I will update my belief somehow. And then it turns out that we have to come up with the same probability.
I see, okay.
Like I assign a priori 0% and you assign 70%.
Right.
And then it depends, but in the end I might assign like a different probability.
Right, right.
So you, like Amon's theorem basically says here that you have to assign the same probability.
That's extremely interesting. I don't know what to say about that at the moment, except to say that you've already added much more structure than was present in my original presentation. And so what we end up saying might be interesting, but it wouldn't actually go against anything I said about the stripped down presentation that I gave.
Yeah, and like, if you allow me, like applied to this situation, like I mean, it's fine to have different like preferences. But now, like if, let's say Yam says it's objectively good and Yak says it's objectively bad, the taste. And now like they meet, and then like one person will find out that it's not objectively good. Like there's at least one person that assigns also like a different taste to that. So like in my opinion, now if they discuss like a third person, that they can objectively ask if he likes or not, so you can perform a test.
Right.
Like you can assign, like both people can assign a probability to that. The third person will say it's good or bad. And then like it seems that they should agree on that, like after discussing. So they find out there's another person who has a different taste. So it's not objectively good or bad. Like there might be chance of 50-50 that the third person likes it or does not like it. So okay, yeah, as a comment.
Okay, you give me something to think about. Thank you. Yeah.
Quick question, a quick follow-up. So, if it can be answered quickly. So, if I understand well, it is crucial to not have a record of the outcome. So, I'm not sure in what sense there is actually disagreement, because how do we actually check whether there is agreement?
It's a logical contradiction. There's no possibility of comparing things. But logic doesn't require comparisons. If we have a contradiction, it doesn't matter that we can't.
Contradiction exists for who?
For anyone who believes that there are outcomes of these measurements.
Maybe I can also, one can have also messages coming out that I see a definite outcome.
Yeah.
Then, of course, you cannot have a record of this.
Without saying the outcome.
That's it. You don't have a record, but you have a proof that there was a record.
Okay, and follow-up question just quickly. I know this is a big topic. If it relies so much on not having a record, then how does this work? Because if I do a measurement, there is going to be a record in my head what the outcome is.
And it will be erased.
It will be erased.
But
And if I write it on a paper, why is it?
it will be erased.
It will be erased.
Yes.
By what is being erased?
Any information about which outcome has been obtained.
So if I write on a paper what the outcome was, you're saying that when, depending on what Wigner will do later, if he does some strange measurement, this would just erase my record.
Well, it depends now what concrete scenario, but it could, for example, go backwards before, like it was a blank paper, and then do something else on the paper and on the observer and so on.
I'm just confused in what sense, if they're going to be erased, the records, if I keep them, then why do we need to say there cannot be a record? I can't make records.
If you keep them, you cannot violate the building requirements. If you keep them, the experiment is enough.
But how can I keep them? You're saying they're going to be erased.
Exactly.
Yes, and
Precisely. This is the point I was raising too. This is the point I was raising too.
But there's still something very strange, because when you think about classical physics and you
say I erase some. When you think about classical physics, and you say I erase the record, then I have a new record afterwards. There is nothing that prevents you to assign a joint probability that there was a definite record in the past and the new one now. And here this is not allowed because of the Bell's inequalities. So it's not just about erasing or not erasing, even to imagine that something existed at that time in the past is jointly with what you see now is excluded.
Okay. Yeah.
I am done with my question. Is there anybody else? No? Okay, let's meet the speaker again. And Tuesday at what time is it? The other seminar?
2 o'clock on Tuesday, I think.
2 o'clock on Tuesday.
But if anyone wants to pursue discussions further today or anytime while I'm here this week, please contact me and I'd be happy to talk to you.